So welcome to today's Gold Seminar. Today's speaker is Jakub Balabán, student of Petrohradiny from Masaryk University, and he will tell us stuff about twinwidth.
Okay. Thanks for introduction and for invitation. As was said, I will talk about twinwidth, more specifically about methods which we use to bound twinwidth of various graph classes, and the method is called the red potential method. So, as many of you probably know, twinwidth is a graph parameter which was introduced in 2020 by these four people. So twinwidth is a graph parameter. You probably know treewidth, which somehow measures how a graph is similar to some tree. So twinwidth is something similar, and it measures similar to cographs. I will later say what are cographs. And so twinwidth can be used to some parameterized algorithms similarly to treewidth, but surely not so many algorithms as treewidth, because twinwidth is much newer, so not so many algorithms have been developed so far. And so what are our own contributions? We use the red potential method twice so far. Once for the case of posets of bounded width, which we used to improve the bound on twinwidth, because it was previously known that posets of bounded width have bounded twinwidth, but the bound was pretty loose because we improved it from this double exponential to linear. And then we use this red potential method also for so-called there should be proper k-mixing graphs, because without the proper they have unbounded twinwidth. So for this class of proper k-mixing graphs, which is like this new class which we introduced because it's a class which generalizes interval graphs, and it generalizes them as much as we wanted to generalize them as much as possible while keeping bounded twinwidth, and they also have a linear bound. Yeah, and now we are trying to use it elsewhere, but so far we have only these two examples. Yeah, so as you see up there, the talk will be in three parts. First some introduction to twinwidth, then the result on posets, and then the result on the mixed-in graphs. Thank you. So first, as I said, twinwidth measures similar to cographs. So first, let me define what are twins. Twins are just two vertices which have the same neighborhood. You may ask, like, does it matter whether there is an edge between the two twins or not? And I say that I don't care. So the precise definition is this: that like twins can be connected by an edge, such as A and B here. Those are twins, and C and D are also twins, like in this graph. Shortly, I don't care whether they are connected by an edge or not. And a cograph is a graph where I can like reduce the graph to a single vertex by identifying twins like consecutively. And in twinwidth, like instead of identifying, because it's too long a word, we say contracting, even though contracting. That's what Bonnet said this in this first paper. It's not my said that it's too long. Yeah, but I will use contracting instead of identifying. So contracting maybe like C and D are also contracted here, even though they aren't connected by an edge. So we say contracting just like first we contract A and B, then we contract C and D, then this, and now we have reached a single vertex, and that means that like all these graphs are cographs, and cographs are graphs which have twinwidth 0. So like in order to define what does it mean to have like some higher value of twinwidth, then we need to allow also contractions of vertices which are not twins completely. But sorry, I forgot. Yeah, we can contract also vertices which are almost twins, or we would like to contract them. And now I need to define the notion of a red edge. This color should be red. Red. So this is a general case. Now there are some red edges from some previous contractions. So now there are like two colors of edges. This black, those are the regular edges of the graph, and those thick red edges. And like if we contract some vertices and they have like a difference in their neighborhood. So for example, D is in the neighborhood of A, but not in the neighborhood of B. and that's why after their contraction, the resulting vertex would have a red edge to D, which somehow means that like there was an error in the neighborhood, like they differ, the neighborhoods differ on D, and we like remember this difference by putting the red edge there. And crucially, we want to remember that there was some problem in the neighborhoods, like onwards in the contraction sequence. So if there was some previous red edge, here between B and E, then we keep the red edge even after the contraction of A and B. And yeah, last case is to see that if it's connected by to both of them by a regular edge, then it stays regular edge. Yeah, formally you can see there like R is the set of red neighbors of the new vertex. Yeah, and what we're interested in is the maximum red degree throughout the contraction sequence. So here is some graph. So sure, at the start there are no red edges. It's just a regular graph with one color of edges, and then we like consecutively contract the vertices until we again reach a single vertex. And yeah, as I said, we are interested in the maximum red degree. So in this contraction sequence, the maximum red degree is 2, because here and here these vertices have red degree. Yeah, red degree is just the number of red neighbors, red edges incident to the vertex. Yeah, so this means that this contraction sequence has red value 2, or here I call it D sequence. So this is a 2 sequence because the maximum red degree is 2. And yeah, twin-width is then minimum over all possible contraction sequences. So this sequence tells us only that the twin-width is at most 2. It could be smaller if we found a better contraction sequence, then it's possibly 1 or maybe even 0. Yeah, so that's the definition of twin-width. So now we may ask, why should we care? Question? Why should we care about something like this? Yeah. And the reason is that in the first paper on twin-width, Bonnet and others have proven that if we have like the contraction sequence of small twin-width of like smaller red value, then we can like decide any first-order formula on the graph. So we can first order means that we can quantify only over like vertices, not sets of vertices. And yeah, so it's like some FPT algorithm. So the function f is like astronomical. It's something like a power tower or something like that. But if it's a constant formula and the twin-width is really small, then it's like efficient algorithm. So it's but like so far it's not practical. Yeah, so this like the main reason why should we care about twin-width, but there are also other results which like connect twin-width to other notions in model theory and combinatorics and something like that, but I will not talk about this. I will talk about these particular cases, as I said at the beginning. Yeah, so some example on twin-width. So that's the twin-width of trees. And the claim is like a simple statement that the twin-width of trees is at most 2. And this is like the algorithm. This is the loop, which like is repeated until the tree is contracted into a single vertex. And we like distinguish 2 cases. If there are like two leaves with the same parent, then we can contract them because it creates no red edges. They are just like after the contraction, no red edges introduced. And the other case is if there are no 2 leaves in the whole tree with the same parent, then it looks something like this. Like this leaf is the single like son of child of its parent. So we contract them, but it introduces at most 1 red edge, namely here to the like parent of the parent, but no edge here, no edge to other child of this parent, because then we would contract first these 2 childs because it would be the if branch. Yeah, so and this can create at most two red edges, because then we might contract, for example, this, and then we would have like this vertex now has a red degree 2, but now it has two leaves with the same parent. So then these 2 are contracted, and so on. So you can probably imagine that this is, if I did it properly, that this would result in a proof that trees have twin-width at most 2. So that's just example how twin-width works. Yeah, so now to the things we studied, and those are posets. So first I will need to define twin width of posets, because we represent posets as the directed graphs, which are transitive, symmetric, and reflexive. So we need a slightly different definition, because the definition I told you is for undirected graphs. But it's not so complicated. We just put a red edge even if they are both connected but in a different direction. So this is a Hasse diagram of a poset, and after contracting A and B, then even though it looks at the first glance that C is in both the neighborhoods, but C is greater than A, but it is smaller than B, so still red edge is there. Yeah, and you know that Hasse diagram, transitive edges are not there, so D is in the greater than A but not greater than B, so also this red edge is put there. So I will not tell you precise definition of twin width for posets. I think it's clear from this. Maybe, or you can ask whenever something is not clear. Yeah, so this is again the result I mentioned at the beginning, that we have proven that twin width of posets of width k is at most 8k minus 9, something linear. I will not go into all details, just main ideas. Yeah, and the main idea is that what does it actually mean about this width? Maybe you don't know. And easily said, it means that the poset can be partitioned into k chains. So it is something these k chains in the Hasse diagram look something like this, some bars between them. So if there are k chains, then the width of the poset is k. And yeah, so our first step is that we fix some partitioning of the poset into chains. The first step of the algorithm for finding the contraction sequence. Yeah, so we have a poset and we want to find the contraction sequence with small maximum red degree throughout the contraction sequence. So the first step is to fix any arbitrary partitioning of the width k, and an observation is that it's good to contract only vertices consecutive in the same chain, because then it's the case in this picture that A and B, so these lines are the chains, and A and B are two consecutive vertices in the same chain, and this means that after the contraction, the chain structure of the entire poset is pretty much preserved, because vertices above B, which are in the same chain, are still greater than this AB, and the same here. So the idea of the algorithm is to do only contractions of neighboring vertices, and then after each chain has been reduced to a single vertex, then we contract the rest to a single vertex, the chains. But that's a trivial end of the algorithm. So for now, we contract only neighboring vertices. And as I said, the idea is called red potential. And red potential is a simple auxiliary notion. It's it's defined for a pair of these neighbors. And it's just the red degree of the vertex if we contracted them to a new vertex. So in this example, the red degree of this pair, the red potential of this pair is 5. Because after the contraction, the resulting vertex would have 5 red neighbors here. Yeah, and the overview idea is that we count the total red potential, the red potential of all pairs in the entire poset. So if we'll have k chains, that red potential of all pairs in all these k chains, and if we manage to prove that this total red potential is small, then it surely means that at least one pair has red potential small enough, and that is the pair we contract. And if we show that the total red potential is small in every iteration of the algorithm, then we can keep finding neighbors to contract until we reach this state, and we then finish it. So how can we prove that the total red potential is small? We can so this is the first step is at the beginning. Now there are no red edges so far. So if there are no red edges in the poset, then then I fix some chain. So I fix this chain U and some other vertex X, which is not in the chain. And we observe that X contributes to the red potential, total red potential of this U. So red potential of all pairs of U. and this x like contributes at most twice, because only to these two possible contractions, because like all vertices above here are like greater than x, all vertices here are incomparable to x, and all vertices here are smaller than x. So x contributes at most two, at most the value 2 to the red potential of u, and this holds of course for every possible choice of x. So yeah, this means that like the red potential of u is this, m is the number of vertices in the whole poset, and like this is the sum. And yeah, if we sum this over all chains u, then we get this. Yeah, it can be seen also that like each vertex, yeah, d is the number of chains. Maybe I called it k before. No, d is the number. Yeah, k is the word. Sorry. D is number of chains, and or otherwise this total red potential value can be obtained as like m choices of this vertex x, and now it contributes to every other chain, and every other chain is d minus 1 possible choices of other chains. Yeah, and I argue that this value of the total red potential is small because like m is usually much greater than d, because like m is it's bounded width, so like the width is small and the poset should be like really like high. So because like in the entire poset there are m minus d pairs of neighbors to contract, then this m minus d should like almost cancel out with this m, and like this would give us something like this constant would be something larger than 2, but basically this should cancel out with this m, because m is much larger than d. So this is like the first step, but as I mentioned, so far I have like ignored the red edges, so we must also like add the contribution to the red potential of the red edges. So as you can see in the picture, like each red edge contributes like at most 4 to the total red potential of the entire poset, because at most to these 4 like pairs of contractions. Yeah, if we count more carefully, then this could be we improve this from 4 to 2, but I will skip this idea. Yeah, and we also had to show that there are only like small number of red edges in the whole poset, but it's not so complicated, so I may show it that yeah, the idea is based on the fact that like 2 red edges cannot cross, like edges going between the same between some two chains, that it cannot look like this, because this edge is red means that like some vertex here was like smaller than some vertex here, because we can imagine these new vertices as like part in some partition of the vertices. So because some vertex from here was greater than some vertex from here, and that would mean that like this vertex should be by transitivity greater than this vertex here. So this is like idea why the edges cannot cross, and using that we show that like there's only a bounded number of the red edges. So if we like multiply this by 4, yeah, so this 10 is like 4 times 2 plus the 2 from the previous slide. So far we have like red potential 10. So I'm skipping some details, but I hope you believe that like using this we can somehow compute the total red potential. But there is still some catch which I didn't mention, because even though if I said that we like in each iteration we find I will go faster. that I said that we can in each iteration find like some pair to contract. So first I contract here, then I contract here, and each time I choose a pair with smaller potential. But there's a problem, because the red degree may grow even if I don't contract that particular vertex. So like here can be a vertex, some x, that like I contracted here, and this gave a red edge to x. Then I contracted here, and this gave a red edge to x. And then I contracted here, and so on. And like the red potential only deals with like a red degree of these newly created vertices. So we had to also like bound the number of red edges which would be added to any vertex, like from contractions which do not involve x. So that's what was on the next slide. Yeah, the first is what I said, that that we have only that mu vertices of smaller degree. Yeah, but that's not so complicated that a vertex may get at most this number of red edges from other vertices. It's actually the same picture as before. Now the semantics is different, that this x is the vertex which is not contracted for some long time, and it can get at most 2 red edges from every different chain, because again, like only these 2 contractions in U may create a red edge to x, and there are d-1 choices of U. So this means that like the red degree of x may grow at most by this value, like by contractions not involving x. So this is like the final piece of the proof. Yeah, now also some lower bound. I will probably skip it. We have like yeah, like it may look complicated, but it's actually like simple picture, simple. Yeah, if you look long enough at it, then you will find the like regularities. But I will skip this. Yeah, that's some technical detail, because I will maybe at the end. Or I will say it's short. That like the twin width of posets was in, like defined as like twin width matrices of the matrix of the like adjacency matrix of the poset, and like it creates red values at the diagonal. So if I have like the matrix, then in the original definition of twin width for posets, there were like red values on the main diagonal, but in the like in my virtual thesis, I define this natural twin width like while ignoring these red loops, so it's just natural well, like ±1. So like it's just this. Yeah, and also there's more with posets of width 2, that they have like twin width at most 2, or without natural at most 3. But this algorithm was not. This is like visualization of the algorithm for posets of width 2, but I will skip it. And because it's not the red potential method as was like advertised. So yeah, and also lower bound for posets of width 2. Yeah, so like conclusion on posets is that yeah, like linear lower and also upper bound like relative to the width of the poset, and for posets of width 2, like it's tight bound, like also two from below and also from above. Yeah, so now I will move to something different than posets, but which and I will try to like connect the method why both the methods are called like red potential method. So first, what are interval graphs? Those are just like interval graphs which are like represented by intervals on the real line. So like here is some line, and I of course draw the interval like not on the same line, but like above, so that we can see like the same color. Like this red vertex is connected to those vertices which like intersects this green line. And important subclass of interval graphs are the proper interval graphs, which means that like no interval is a subinterval of another. So this is the case, I think, of proper interval graph. Yeah. Yeah, and the difference relative to twin width is that like general interval graphs have unbounded twin width, and like these proper interval graphs have twin width at most 2, was shown not by us. But we, as I said, we will generalize these interval graphs to this proper k-mixed graphs, which is like some really complicated generalization, because, as I said, we wanted to generalize as much as possible while keeping bounded twin width. So yeah, I will. Yeah, and because already interval graphs have unbounded twin width, so that means that if we generalize them, then they still have unbounded twin width. So I will talk only about the proper case. So if I sometimes forget to say proper k-mixed graphs, then I mean proper. I just didn't want to say this one word. So this is the definition. Yeah, that's just for illustration. I will explain it on a picture. Yeah, so this is an example of a proper three mixed-in graph. You can like generalize it in your head for arbitrary value of k. So so this value 3 means that like the graph can be partitioned into 3 like parts, which like have some properties. And like the intuition is that now the interval-like structure may be only local. Like in interval graphs, the interval structure is like global throughout the entire graph. And now it's somehow local, like inside each of these parts. So these are like these first 3 lines. But like we don't need them to be interval graphs. We can also they can also be complements of interval graphs. So that's the case like in this blue color. Then you can see that like this A and B are like those intervals like interleave, but there is no edge between A and B. But that's because I illustrated here then that it's a complement of interval graph. Like these two is also just interval graph, just small example for like illustration so that it fits on one slide. Yeah, so just like between inside these 3 parts, it's an interval graph or a complement. And we also need the interval structure like between each pair of these parts. So like between blue and red, green and blue, and green and red. And yeah, again, it can be like it's called I think big interval graph or something like that. It's like also this interval representation, but it's a bipartite graph. So we like edges inside blue are decided here. Like edges inside one part are decided in these first 3 lines, and here are decided like which edges should be there between the parts. And yeah, again, it can be complemented. So this slide is complemented, and we somehow need like the ordering of the intervals to be the same as in the inner ordering or inversed. So you can see that like this 1, 2, 3 is in the same order as like the order here, but here like red relative to green is inverse, so it's 3 to 1. So it's like cannot be arbitrary ordering, like 3, 1, 2 would be wrong, so it wouldn't be the definition, but it's like either the same relative ordering or inversed. Yeah, and that's basically all of it. Yeah, so just proper k-mixing graphs means that like all these representations are proper. Yeah, and yeah, so that's the definition. Yeah, some example, if you know, yeah, I didn't mention it, but like our k-mixing graph, so why should we call it this way, is that it's like further generalization from just thin graphs, and like without the word mixed, it means that like all these orderings are just suborderings of some global ordering. So that's the thin graphs. If you see it somewhere without the word mixed, then it means this. So of course, if you have one thin graph or one mixed in, then it means that we have only one part. So it's just interval graphs. And yeah, in the case of 2, then we cannot use the mixing anywhere. So it's the same if we use mixed or not. And from 3 onwards, the mixed in graphs are more general. Yeah, and this is another view on the interval graph. This is just adjacency matrix of some interval graph. Yeah, and this view I will need it later for the twin width proof. Yeah, it's ordered like the rows and columns are ordered in the same way as the intervals in the representation. So it means that like, yeah, of course, the main diagonal is 0 because the graph is simple. And for example, here on this like middle column, it means that like this vertex is not connected. Then there are some vertices, these ones, which are like have non-empty intersection with this vertex. And then from some part on, it's zeros again. So it's like zeros. If I look at some vertex, it's zeros, then ones, and then sometimes later maybe zeros again. So yeah, so I will use this property of interval graphs later. Yeah, so some examples of this, of like instances of our k-mixing class are, for example, again, trees or grid graphs. Yeah, we generalized also from like these two-dimensional grids also to higher dimensional grids. So if the dimension of the grid is constant, then it also is like proper k mixed in for some k, depending on the dimension of the grid. Yeah, but we already know that like these trees have bounded twin width. I showed you at the beginning, and like grids were also known to have bounded twin width. So like, why should we care that these proper k mixed in graph have also bounded twin width? And this is like more just this class of intersection graph of paths on some fixed graphs, which is again some technical definition, and they are also like k mixed in for some constants depending on the graph. Yeah, but why do I say is that this class is proper k mixed in for some k, and it means that it has bounded twin width, and it wasn't known previously that this class is bounded twin width. So that's just motivation for why it really says something new. This result that proper k mixed in graphs have twin width at most 9k. And yeah, again, I didn't mention it in the case of posets, but we can find in the posets it was surely algorithmic result that we can find the contraction sequence like algorithmically efficiently in polynomial time, and it's the same case here. But we must be given the representation using all these like using this partition and these intervals and order and these orderings. Yeah, without the representation, if someone just tells us this graph is 5 mixed spin, then we cannot. We must be given the representation for the algorithm. Yeah, and the proof that it has bounded twin width again uses some similar idea to the red potential, but this time, yeah, previously it was like red potential between like pairs of consecutive vertices in some chains in the like Hasse diagram of the poset, and now it's like consecutive rows in the adjacency matrix. So like this is just how twin width works. If we view it in matrices, we just contract those rows and columns. We must like contract corresponding rows and columns at the same time. So like A and B are merged together. Just instead of red edge, I put this R entry in the matrix. Yeah, but the definition of twin width is the same. It's again the maximum red degree of some maximum red degree over all rows and columns. So this is how the idea goes. Is that as I showed you this image of this matrix, so this was for interval graphs, and like these k-mixed graphs have the interval structure like inside each part and also between them. So that's like intuition why it should hold that the matrices have like this property like in every submatrix. So we like order each rows and each columns like surely of course in the same order, but the order represents the part. So this is just even more simple example than before. This is just two mixed in graphs, so just T5, just circle, and it's like these two parts, and like each like these four submatrices. So like this submatrix corresponds to like the interval representation of the green part. This submatrix corresponds to the interval representation of the inner interval representation of the blue part, and like these two submatrices are the like the intervals between the two parts. And because like each of these four submatrices are like interval or pseudo interval graphs, then they still have the property that it's like zeros, then ones, then zeros. But because we use the complementation operation, then it may be like swapped, that it's first ones, then zeros, then again ones. And because of this inversion operation that we like inverted the orders of the vertices, then the diagonal boundaries, so-called, may be also inverted, that they don't have to go from like this corner to this, but they can go from this to this. Yeah, maybe it's better seen in this picture. It's like this. This is like a it's like one third of a big matrix, which should be like 3 times 3 of these like submatrices. And yeah, this is the main diagonal. So like it's the bottom third. So the matrix like continues up here, and like you see that like in each like of these sectors there are only ones and only zeros. So that's if you understood it in the interval graph case, that it should be like zeros then ones, because the interval like somehow doesn't interleave them, then it like intersects them, and then it doesn't. Then it's the same thing, just generalized over this like more general class, which has the interval graph, interval-like structure only locally. And the idea is that the red edges, those are these R entries, they can be only next to some diagonal. Because, for example, if I contracted here these two rows, then like these two rows, then these entries would remain zero. They are like not next to any diagonal, this diagonal boundary. So like they remain zero, and like these R entries can appear only here because it's because the diagonal boundaries like are between those zeros and those ones. And like we prove it by induction that these R entries like are always only next to a diagonal boundary. So like after some contractions, the boundaries are moved, and it holds the property holds that the R entries are still only next to some diagonals. And yeah, I didn't say what are these numbers. Those are the red potentials, because this is 7, and it means that like between the first and the second row there are like 7 these diagonal segments. So it's like 1, 2, 3, 4 in the first submatrix, and then 3 here. So like this 7 means that after contraction of these 2 rows, at most 7 new red edges, like the red degree of the new row would be at most 7. And the same holds for the other. So this is the red potential, and we used it also like similar way as before, that the total red potential, using this property that the red entries can be only next to the boundary, and the boundary has like bounded length, because the boundary must go from like one corner and it goes somehow, yeah, then it continues like this. Like the boundary has length at most this. Yeah, that holds for like there are like 2 boundaries in each of these submatrices. So there's like constant number of boundaries, and important thing which I didn't say is that like this we want like at most as many values here as possible. So we choose like this big row. We choose the row with many rows, because if the big matrix looks like this, and so it may be like this, yeah, so it of course must be symmetric. So I will try to draw it symmetrically. Yeah, so these are the like big submatrices. So it's like four mixed in, because there are like four subparts. Then it's like good to try to contract something in the first big row, in the first like this, because there are like many rows. So like then the red potential is divided between the total red potential is divided between many rows, and this means that we can find some pair of rows to contract which has smaller red degree, because there are like many, because it's like high, the submatrix is high and not so wide. Yeah, so maybe I'll leave it to questions. Maybe I've lost all of you. So that's all, I think. Yeah. So like conclusion is that this I'm not sure if I was successful at like showing the similarities between the why it's both called red potential, but that was my idea, that that like we like averaged some value called red potential between like pairs of neighbors, and then something similar between like pairs of consecutive rows in these matrices. Yeah, and the question is that like could this red potential method be like used somewhere else as well. Or, as I said, we would like to be able to recognize these mixed in graphs so that we can find the twin width even without being given the representation. Yeah, so that's all for me. Thank you for your attention. I'm ready for some questions.
I wanted to ask, so you said that if it's the H graph, like intersection graph of paths in subdivision of H, then it's a mixed in graph. And can we also build like algorithmically the representation in this case? So is it for your algorithm
Yes,
you need
yes.
a representation as a k-mixed graph?
Yes, for this case we can build a representation.
Okay.
From the graph. Like if we are given, I think if we are given the representation like the path representation.
And my second question, it somehow seems to me that this somehow captures the essence of mixed in graphs. So is there a chance to like maybe go the other way around? So show that every k mixed in graph can be represented like this?
Yeah, we didn't think about it. I think that may be possible. Yeah, like this result is not mine, it's by the Hunzaidelski, so like I didn't like invent this connection, but I think that he also didn't think about the opposite direction, so thank you. But I don't know.
Yeah, maybe there would be problem with these complements and like opposite directions.
Yeah, maybe.
Somehow it seems to me there can be some connection.
Another question?
Sure. So this is like an n squared mixed in graph. Like,
yeah,
I'm not from your world, so
yeah,
for me, n is like huge number, right? For example,
no, sorry. M is now number of edges in the underlying graph. So this is like
4 in this case.
For this case, yeah. In the poset case, it was number of vertices of the poset. Sorry. Yeah. Now we have like this underlying graph. It's this. It's the black graphs, and now we have like
K is the
K is the number of distinct paths in this graph. Yeah. This is the H.
At most then in this case.
1, 2, 3.
It's too much counting.
Yeah. I would guess at most then, yeah.
Other questions?
Do you have any lower bounds for the mixed thin graphs? For the twin width of the mixed twin?
Yeah, we don't have it in the paper. Yeah, we probably don't. Huh. Yeah, no, I don't know. Yeah, we probably don't have. Yeah. Maybe some.
Are copies? Those are not in this class.
Yeah, like graphs in this mixing graph class.
Our bound of 0 is not so.
Yeah, like 0. Yeah, like of course.
I'm not sure whether cographs are not.
Yeah, but what you can show is that there is a k-mixed graph with this high.
Yeah, like we would get something like with like also the linear, because in the case of posets we had also linear lower bound. So yeah, we don't have it yet. We can think about it.
No, but what I asked is stupid. Interval graphs are a subclass of this. And
Yeah,
interval graphs are the natural ones have a twin width of 2.
Yeah. Yeah, but I thought you asked like whether there exists some like proper k-mixed in graph with at most k. So that's what we don't have.
Do we have other questions?
is your intuition that recognizing mixed-in graphs is going to be an easy problem or not?
Yeah, currently I think that it's hard, but like I haven't like been working on it that much.
Okay.
But like my intuition is not so good as like that. Yeah.
All right, so let us thank the speaker again.